Imagine one day when humanity could reach out and pluck the stars from the sky, or gently guide the planets drifting through the vastness of space. That is not merely a poetic dream, but could be the portrait of the future of super-advanced civilizations. Scientists have proposed a hypothesis. If there are other civilizations in the universe that arose millions of years before us, what would they look like? What would they do with their own stars? Perhaps they have already built enormous Dyson rings to capture all the light of their suns, and then gone even further, learning how to siphon plasma from stars, transforming that very matter into energy for life. The miracle is that by consuming a star, they do not destroy it, but make it live longer, slowly, steadily, like a breath extended across infinite space. They are no longer conquerors of the cosmos, but gardeners of the stars, nurturing, adjusting, arranging the rhythm of the galaxy. To decode those hypotheses, let us explore together the special stars of the vast universe, the limits of humankind, and the distance between us and other civilizations. There is a quiet moment in the history of thought when humanity first looked beyond survival and began to measure possibility. It happened in 1964 when a Russian astrophysicist named Nikolai Kardashev dared to ask a question that still echoes through the deep. What defines a civilization not by its morals or art, but by the energy it can command from the cosmos itself? Imagine drifting slowly past the edge of our solar system. Behind you, Earth is a pale shimmer. Ahead, stars burn like breathing embers. In that endless silence, Kardashev imagined a ladder, a cosmic hierarchy of power. Each rung marked not wealth or conquest, but mastery over nature's fuel. The first rung, Type belongs to a civilization that can harness all the energy available on its home planet. Oceans, winds, volcanoes, the full light of its sun, everything that touches its world becomes a part of its pulse. By comparison, our species has barely begun the climb. We still tear into the crust for fossil remains of ancient sunlight, transforming them into brief warmth, short-lived motion. We hover trembling at Type 0.7, civilized enough to light the sky, but still at the mercy of storms and darkness. The second rung, Type 2, is something the human mind can describe but cannot build. It belongs to those who surround their star with a vast mechanical shell, a Dyson sphere to harvest nearly every photon it emits. Such a civilization would no longer need planets. It would live in the glow of its own captured sun, turning stellar fire into civilization itself. To them, the star would not be worshipped, it would be engineered. The third rung, Type 3, extends the dream to a galactic scale. Imagine a species so advanced that the total output of billions of suns flows through its machines. They could sculpt the arms of galaxies, ignite nebulae, or drain the light from entire clusters to prolong their own existence. From our viewpoint, such entities would be indistinguishable from the universe itself, moving slowly like tectonic thoughts across eternity. Kardashev's scale was elegant, seductive, and deeply human. It turned the unknowable into a sequence of numbers, a stairway we could imagine climbing. Yet even as it inspired generations, the cracks in its perfection began to show. Could energy truly be the sole measure of advancement? Could a being's greatness be reduced to how brightly it burns the stars around it? In time, critics began to see the scale not as a prophecy, but as a limit. Physics itself rebels against infinite appetite. A complete Dyson sphere would collapse under its own heat. Its materials would vaporize, its orbits decay, its creators destroyed by the very light they sought to own. Total efficiency is not an achievement, it is a paradox. Modern thinkers reimagine the scale as a theoretical boundary, a horizon beyond which the laws of reality may fracture. Perhaps civilizations do not rise forever. Perhaps beyond a certain point they must learn to consume differently, not brighter, but deeper. What if the next step on Kardashev's ladder does not climb upward toward light, but inward into the heart of stars themselves? What if a civilization could draw power not from radiation but from matter, from the plasma, the core, the burning substance of suns? Such thoughts lead into the realm of the starvores or stellar predators, beings who no longer harvest starlight but drink directly from stellar veins. Their existence remains unproven, their signatures perhaps lost among the ordinary rhythms of binary systems. Yet in the silence of space where energy and time intertwine, it is not impossible to imagine. Because Kardashev's question was never about others. It was a mirror held up to us to see how small our reach remains, and how infinite our desire to touch the fire that made us. Somewhere in the quiet margins of theoretical astronomy a strange word appeared. It sounded almost predatory: Stellivore, a fusion of two others, star and carnivore. It described not a creature of flesh, but a civilization whose hunger had outgrown light itself. If the Kardashev Scale was a ladder, the Stellivore hypothesis was the moment that ladder broke through its top rung. It was born from a simple question: what happens when light is no longer enough? A Type 2 civilization in theory already captures the full radiance of its star through vast solar structures, Dyson swarms or mirrored satellites. But even this perfection hides a flaw. A star radiates energy outward, scattering power into the cosmic night. No structure, no matter how immense, can truly seize it all. There is always loss, always waste. And for a civilization that has already filled every orbit with cities, every moon with machines, and every second with need, inefficiency becomes starvation. So they turn inward, not toward darkness, but toward the star itself. They begin to reach beneath its surface to lift harvest and reshape its burning skin. This process has a name: star lifting, a concept that exists not in fantasy, but in the mathematics of plasma physics. In theory, a star's matter, hydrogen, helium, heavier traces of carbon and iron, can be drawn away by manipulating its magnetic fields. Massive superconducting loops or directed plasma flows could peel off layers of gas and channel them into controlled streams. Each ton of that matter carries unimaginable power enough to sustain a planet for centuries. The technology would not just capture light, it would manufacture it, redirect it, compress it, and use it as fuel for worlds orbiting in the dim glow of efficiency. The logic is brutal yet elegant. By slowly removing the mass of their sun, a Stellivore civilization would make it smaller, cooler, and longer lived. Stars burn faster the more massive they are. By trimming that mass, their creators prolong their host's lifespan, granting themselves tens of billions of extra years of energy. It is a paradox of mercy and consumption, the predator that keeps its prey alive to feed forever. How would such beings appear to us? Not as spaceships or signals, but as anomalies. Stellar systems behaving in ways our equations cannot explain. Astronomers already watch pairs of stars where one seems to be devouring the other: white dwarfs, neutron stars, black holes pulling matter into glowing spirals of death. But those are natural blind processes of gravity. What if among them there exists one system whose symmetry is too perfect, whose rhythm is too steady, whose consumption lacks chaos? That might be the mark not of a monster but of intelligence. To the human eye it would look like any other binary star. To a careful observer it would whisper precision. Gas siphoned not in bursts but in constant measured flows. Temperatures balanced, emissions tuned. A stellar predator camouflaged as a patient scientist. There are theories, unconfirmed, fragile, that some civilizations could even use the harvested plasma for propulsion. Imagine colossal engines built from captured matter, expelling light itself to sail between stars. Each journey a migration to a new feeding ground. Each voyage a step closer to the galactic scale once imagined by Kardashev. But beneath the science lies something quieter, almost philosophical. A Stellivore does not conquer through fire or war. It evolves beyond consumption of planets, beyond dependence on radiation, until its home star becomes both heart and harvest. It is a reflection of every civilization's dilemma. When survival demands more than nature intended, what remains of reverence? Perhaps in their pursuit of energy, the Stellivores have also mastered patience. They do not rush. They drift from one sun to the next, gathering light not as plunder but as memory. And when their stars finally dim, they move on, leaving behind nothing but a faint pulse in the dark, the quiet heartbeat of a civilization that once ate light to keep dreaming. Energy is never just about power. It is about survival. Every species that rises high enough eventually meets the same mirror, the hunger of its own existence. For the imagined Stellivore civilizations, the stellar harvesters, this hunger becomes both their drive and their destiny. To consume a star is not an act of greed, it is an act of continuation. Their purpose in the purest sense may be as simple as ours, to endure the cold eternity that waits when all suns fade. In that context, the feeding becomes preservation, a method to stretch cosmic time itself. The first goal is obvious energy extraction. A single gram of stellar plasma contains energy far beyond the scale of chemical or even nuclear reactions on Earth. By tapping directly into this raw furnace, a civilization could power entire worlds, or drive interstellar vessels propelled by fusion itself. Plasma lifted from the stellar atmosphere could be compressed, stored and converted into directed streams, a source not only of heat, but of thrust. It is the ultimate sustainability, not stealing from planets, but borrowing from the star's own pulse. But there is a second, subtler purpose: longevity. Stars are ephemeral even if they outlive civilizations. A star's lifetime is dictated by its mass. The more massive the star, the faster it burns its fuel, collapsing in a final blaze. By delicately removing material from their host layer by layer over millions of years, a Stellivore civilization could slow that burn. Less mass means lower pressure, lower fusion rates, and a lifespan extended by billions of years. The predator paradoxically becomes a caretaker. It drains its host so gently that the star lives longer than it would have without intervention. This balance between survival and mercy is almost poetic. It suggests that even in the cold logic of physics, there might be ethics written in plasma and magnetism. How then could we detect such an entity? Astronomers have begun to look for the strange and the symmetrical, the quiet impossibilities hidden in data. If a civilization were lifting matter from a star, its light would flicker, not with chaos, but with consistency. We might see spectral lines shift as elements are stripped away. The star might lose mass faster than nuclear models allow, yet remain stable. Its emissions subtly altered, its corona unnaturally ordered. Binary systems already display such behaviours. White dwarfs feed on their companions, pulling gas in glowing streams that form accretion disks. But these natural predations are turbulent, irregular and violent. A star's signature would be different. No explosive bursts, no random jets, only a disciplined, continuous siphoning. An unchanging rhythm, a heartbeat with no pulse of chance. To the untrained eye, it would look like an ordinary system. To a patient observer, it would whisper the difference between nature and intention. Perhaps we've already seen such systems and simply filed them under anomalies. Maybe the universe has been showing us the fingerprints of intelligence for decades, hidden in the symmetry of starlight. There are instruments today, like the James Webb Space Telescope, capable of measuring these subtle deviations in luminosity, temperature and chemical spectra. One day, in the vast datasets of countless suns, someone may notice a pattern that doesn't fit thermodynamics, a balance too perfect to be chance. And when that happens, the discovery will not be of a new star, but of a civilization performing a slow cosmic surgery, a dance of light and gravity far older than our species. Until then, we keep searching. Not because we expect an answer, but because the act of looking defines us. We're in our own small way apprentices of the same craft, drawing power from our world, extending our time, hoping that one day someone far away might notice the symmetry of our light and wonder who we were. Far beneath the river of the Milky Way there drifts a companion, pale, ghostly and ancient. It hangs in the southern sky like a torn fragment of light, a cloud mistaken by early sailors for a wisp of mist. We call it the Large Magellanic Cloud, or LMC, a neighbouring galaxy small and luminous, once thought to orbit our own like a faithful moon. But the truth revealed by modern telescopes tells a quieter and far lonelier story. The LMC is not a permanent companion. It may not even be bound to us at all. Recent measurements from the Hubble Space Telescope suggest that it is merely passing by a traveller, caught in a slow gravitational encounter with the Milky Way brushing past before vanishing into the dark. The data shows its motion clearly. The LMC once approached us, reached its closest distance, and now begins to drift away, pulled by tides of invisible matter. To understand what this means, one must first imagine the hidden anatomy of a galaxy. Every spiral, every cloud of stars is wrapped in a vast halo of gas, tenuous, invisible and immense, stretching far beyond the visible disk. This halo is not just decoration. It is the galaxy's reservoir, the breath that feeds its newborn stars. Without it, the galaxy eventually goes still, fading into quiet retirement. Hubble's ultraviolet observations revealed that the halo of the Large Magellanic Cloud is not what it should be. Compared to galaxies of similar size, the LMC's halo is 10 times smaller and 10 times less massive. Somehow, much of its gas, its lifeblood, has been stripped away. Astronomers believe this theft occurred when the LMC passed near the Milky Way's own gaseous halo. The two invisible envelopes collided, pressing against each other like slow cosmic winds. The denser halo of our galaxy pushed against the smaller one, sweeping its gas backward into a long, shimmering tail. It is a collision without sound, a storm that lasts millions of years. Now, as the LMC moves away, it trails that stream of stolen gas behind it, a plume stretching for tens of thousands of light years. From afar, it resembles a comet's tail, luminous and delicate, drifting in the intergalactic dark. But unlike a comet, this tail is not frozen water. It is hydrogen glowing faintly under the touch of ultraviolet light. The loss of so much gas foretells the LMC's slow decline. Stars form only when clouds of hydrogen collapse under their own gravity. With its reservoir depleted, the galaxy's ability to give birth to new suns weakens. Its future generations of stars will grow fewer and dimmer, until one day it stops creating them altogether. When that happens, the LMC will not die in flame, it will simply fade, leaving only the ancient stars that still remember its youth. And yet there is resilience even in loss. The LMC has managed to hold on to part of its gas enough to sustain star formation for a while longer. Its brightest clusters, such as 30 Doradus, the Tarantula Nebula, still roar with stellar birth. Inside that nebula, massive stars ignite and die in mere millions of years, carving the gas around them into glowing filaments. It is both cradle and graveyard, a reminder that creation and decay are one breath apart. Eventually, the gas stripped from the LMC will not be lost forever. Gravity, patient as always, will pull it toward the Milky Way. Over cosmic time, our galaxy may absorb that material, feeding its own cycle of creation. In this way, one galaxy's loss becomes another's renewal. The universe wastes nothing. So when you look up at the faint cloud in the southern sky, remember what you see is not just a companion to our galaxy, but a witness to collision, erosion and rebirth. The Large Magellanic Cloud drifts onward, not defeated, only transformed, its light carrying the memory of the moment two galaxies touched and exchanged breath across the void. Somewhere beyond the reach of our solar system, a planet glows like an ember, adrift in the dark. It circles its star so closely that a single year there lasts less than 2 days. Its surface is molten rock, its skies heavy with storms of sulfur. To the instruments of the James Webb Space Telescope it flickers faintly, but inside that faintness lies a secret: this world may be alive with fire. The planet is what astronomers call a super-Earth, a rocky body larger than our own but smaller than Neptune. From such worlds light barely escapes. They do not shine, they only reflect. And yet when their orbits cross the face of their stars, starlight filters through their atmospheres, carrying clues in its spectrum. Each chemical element leaves a fingerprint, a whisper etched into the light. When scientists studied that whisper, they found something unexpected: signs of sulfur dioxide, SO2 and hydrogen sulfide, H2S, the same gases that rise from volcanoes here on Earth. But this planet orbits so close to its star that its surface could melt lead. At such distances, oceans cannot exist and clouds cannot form. Only one force could be painting those chemical scars across its sky's volcanism on a planetary scale. The mechanism is violent and precise at once. As the planet swings around its sun, tidal forces twist and stretch its interior, the way the moon pulls the Earth's oceans, but with far greater fury. This constant flexing heats the mantle from within, cracking its crust, forcing molten rock to the surface. Eruptions may cover continents, pouring rivers of magma that never cool. From orbit it would gleam red gold, wrapped in a thin atmosphere of smoke and lightning. Astronomers compare it to Io, the tortured moon of Jupiter, our solar system's most volcanic world. Io's surface is scarred by hundreds of eruptions, its plumes rising hundreds of kilometers high, driven by the same tidal forces. But where Io's heat comes from a single giant planet, this super-Earth endures the pull of an entire star. Its oceans of rock boil endlessly, reshaping the planet's face with every orbit. The discovery reshapes how we imagine distant worlds. For centuries, humans pictured alien planets as frozen or lifeless barren stones under pale suns. Now telescopes reveal places where the ground itself breathes fire. And with every observation we come closer to understanding that volcanoes may not just be symbols of destruction, they are engines of creation. On Earth, volcanic eruptions release gases that build atmospheres, minerals that seed oceans, and heat that fuels chemistry. They are the architects of habitability. So when astronomers detect sulfur-rich skies around a faraway planet, they are not just finding chaos, they are witnessing the conditions that once made life possible here. Perhaps such a world, given time and distance, could cool. Its lava seas might crust over its toxic vapors, settle into oceans of acid and salt. and deep within those turbulent beginnings, chemistry might begin to whisper the first steps towards self-replication, the fragile art of life. For now, we can only watch. Through the filters of Webb's instruments, we see a thin line of light trembling as the planet passes its star. In that trembling lies a story of heat motion and endurance, a reminder that even in the farthest reaches of the galaxy, creation never stands still, it burns, it reshapes, it begins again. And somewhere among those unseen fires, perhaps another observer in another sky looks back toward our sun and sees the faint signature of our own volcanic world, our Earth still alive, still breathing beneath its clouds of blue and white. In the dim corridor between Jupiter and Neptune drifts a strange wanderer, neither comet nor asteroid but something in between. Astronomers call it 29P Schwarzmann-Wachmann, though to most it is simply Centaur 29P. It moves slowly, its orbit wide and uncertain, as if it cannot decide whether it belongs to the frozen outer darkness or the warmer inner system. But what makes 29P remarkable is not its path, it is its pulse. Unlike most icy bodies that sleep for eons, 29P is alive with motion. At irregular intervals, sometimes weeks, sometimes months, it suddenly brightens, flaring hundreds of times brighter than before, and then just as quickly it fades again into the quiet cold. Each flare is a whisper from within a frozen volcano erupting in silence across 1 billion miles of emptiness. These eruptions are not made of fire, but of ice and gas. They are called cryovolcanoes, volcanoes of the cold. Where Earth's volcanoes bleed molten rock, these distant mountains exhale liquid nitrogen, carbon, monoxide, methane and water vapor. On 29P, sunlight is weak but relentless. Over time it seeps through the crust, warming buried pockets of volatile ices until the pressure builds high enough to crack the surface. And when that happens, the eruption begins. In less than 2 days, Centaur 29P can unleash 3 massive outbursts, each releasing more than 1 million tons of gas and dust into space. The plumes expand, reflecting sunlight and turning the object from a dim speck into a glowing ember, visible through small telescopes. For a brief moment it shines 300 times brighter, a comet without a tail, a volcano without heat. Scientists have tried to model the rhythm of these explosions, but no equation quite fits. The vents seem to open and close unpredictably, as though 29P breathes in slow, uneven patterns. Its rotation may shift, its crust may crack anew, buried ices might rearrange as they melt and refreeze. It is not chaos, it is evolution happening on the smallest scales of temperature and time. To imagine it, picture a landscape of endless night, a crust of dirty ice stretching for hundreds of kilometers marked by craters and fractures. Beneath that crust, reservoirs of carbon monoxide and methane simmer, under pressure trapped since the dawn of the solar system. When a beam of sunlight reaches just deep enough, a chamber bursts open. A geyser of vapor erupts into the void, expanding into a white halo before dispersing into nothingness. And then silence returns. 29P is more than a curiosity, it is a window into the early solar system. Its chemical makeup mirrors that of comets formed billions of years ago before planets even existed. By studying its plumes, astronomers read the oldest diary in the solar system, one written in ice instead of ink. Every eruption exposes material unchanged since the time when the sun was still surrounded by its original disk of gas and dust. Yet there is something strangely poetic about it too. This tiny world 500 million kilometers from warmth still moves and breathes. Its eruptions remind us that creation does not belong only to light and fire, it also belongs to cold and pressure, to silence and waiting. The same processes that once shaped Earth's volcanic heart continue here, transposed into another register, played in the key of ice. Perhaps in that frozen rhythm lies a message that energy is not confined to stars nor life to heat. Even in the chill beyond Jupiter, motion endures, pressure builds, and something inside refuses to sleep. So the next time a telescope catches the sudden brightening of a distant point of light, remember that you are witnessing the heartbeat of a frozen world, a cryovolcano erupting against the dark proof that even in the outer shadows of the sun, the universe still dreams of movement. In the grand halls of Washington, where laws are written and futures are debated, another kind of question once echoed, one that had nothing to do with taxes, wars, or borders. It began with silence. Then in front of cameras and the watching world, an officer spoke of objects in the sky. The year was recent, but the story felt ancient. For as long as humanity has looked upward, there have been lights we could not name. We called them omens, then miracles, then mysteries. Today we call them UAPs, unidentified anomalous phenomena. The word itself is new. It replaced UFO, a term too heavy, with decades of myth and conspiracy. But the mystery remained the same. What are we really seeing up there? Inside the US Congress, for the first time, the question became official. There were witnesses, transcripts, and televised testimony, an attempt to bring reason into the realm of wonder. And at the centre stood a man named David Grush, a former intelligence officer, calm but deliberate in his claims. He told the assembly that certain US agencies had recovered not just objects of non-human origin, but biological entities as well. He did not offer proof, only conviction, and a quiet certainty that left the room tense. Others joined him: Louis Elizondo, a former Pentagon investigator who once led the EATER Advanced Aerospace Threat Identification Program, and a retired admiral who hinted at technologies beyond known physics crafts that could move in ways no engine should allow, turning at impossible speeds without visible propulsion or heat. They spoke of classified data radar signatures, objects that seemed to dive into oceans and rise into space, crossing air, sea and vacuum as if the boundaries of matter meant nothing. And then came the rebuttal. Across from the witnesses sat Dr. Sean Kirkpatrick, director of the Pentagon's official UAP office, AARO, the All-Domain Anomaly Resolution Office. His tone was measured, his answers clinical. Yes, he said, there are hundreds of unexplained sightings. Yes, some of them defy immediate identification. But no, there is no credible evidence of extraterrestrial technology. Most cases, he added, turned out to be ordinary things mistaken for extraordinary ones. Weather balloons, drones, birds, debris, optical illusions. The unknown, he reminded the room, is not always the unearthly. Still, the hearings marked a turning point. For the first time, talk of strange aerial phenomena had stepped out of late-night radio and into the congressional record. It was no longer just science fiction, it was science under oath. The room itself became a metaphor for humanity's divided spirit. One half demanded proof, the other half already believed. And between them lay the vast grey sea of uncertainty, shimmering like heat above a desert runway. Outside those chambers, astronomers continued to search for technosignatures among the stars, laser pulses, artificial gases, the faint rhythm of civilizations perhaps long dead. Meanwhile, pilots reported metallic orbs and glowing triangles that tracked their jets without engines or trails. Satellites caught flashes that no algorithm could classify. Each side gathered data. Neither found peace. Maybe the truth lies not in evidence, but in the persistence of our gaze. Every generation rediscovers the same question: are we alone? And perhaps in the asking, we show the universe something more remarkable than any answer, a species that refuses to stop looking even when the stars remain silent. As one congressman murmured after the hearing, the sky is not just blue anymore, it's a question. Magnetism is the unseen hand of the universe. It bends light, sculpts galaxies, and whispers through the smallest grains of dust. Yet for all its power, its origin remains one of the cosmos's oldest riddles. Where did the first magnetic field come from? What spark lit this invisible fire between the stars? Everywhere we look, magnetism is there. It coils around our planet, protecting life from solar wind. It threads through the sun's corona guiding flares that dance like ghosts of fire. It winds through nebulae galaxies, even the vast empty spaces between them. The cosmos hums with fields that shape motion, radiation, and time itself. But these grand magnetic patterns did not always exist, they had to be born. Astronomers call the earliest form of this force the seed magnetic field, a faint and fragile current that once flickered through the newborn universe. Its traces may still linger between galaxies today, so weak that only polarized light can reveal it. But how could such order emerge from chaos? To find the answer, scientists have turned to dust the smallest architect of the cosmos. This is the dust battery hypothesis. After the first stars lived and died, their supernovae scattered heavy elements into the void, forming dust grains, tiny irregular bits of carbon, iron and silicate. When starlight strikes those grains, it pushes on them unevenly, because each grain carries a tiny electric charge. As radiation pressure drives them through the surrounding gas, the electrons and ions separate ever so slightly. That separation creates a weak electric current, and where there is current, a magnetic field is born. It begins almost imperceptibly, an electrical sigh moving through the dust-laden clouds. but time and turbulence magnify it. Cosmic winds twist it into filaments. Collapsing gas amplifies it as stars ignite. Over eons, the weak seed grows like veins spreading through a galactic body. Soon, entire spiral arms of galaxies shimmer with magnetic threads, invisible to human eyes, but carved deeply into the fabric of space. We detect these fields not by touch, but through polarization light that vibrates in a single direction after passing through aligned dust. By studying that light, astronomers map the orientation of fields tens of thousands of light years across. It is a cosmic calligraphy written in magnetism and read by light itself. But the mystery deepens when we look to the most extreme regions of all the hearts of galaxies where black holes dwell. These monsters, by definition, cannot emit magnetic fields from within. Nothing escapes their event horizons, not even information about spin or charge beyond the simplest constants. Yet we see something impossible: jets of matter erupting from their poles, stretching millions of light years into intergalactic space guided by intense magnetic lines. The paradox is clear: the source of magnetism cannot be inside the hole, so it must be born around it. Here lies the second revelation: black holes may inherit magnetism. Before a massive star collapses, it often becomes a neutron star, an object so dense that a teaspoon of it outweighs mountains, and so magnetic that it can strip electrons from atoms light years away. If such a neutron star collapses further into a black hole, its fierce field cannot follow it into the singularity. But the surrounding plasma disk, the accretion disk, can still carry the memory of that field. As the black hole forms, the field lines remain anchored in the swirling matter around it, drawn taut by rotation and gravity. They twist into spirals, focusing energy into twin beams that blast outward at near light speed. Scientists call this inheritance the poetic name hair from mom. The mother star's magnetism surviving in the child's violent birth. So from dust to galaxies, from collapsing stars to the edges of space-time, magnetism endures. It binds the smallest particle to the largest structure, as if the universe itself refuses to forget its first electric breath. Perhaps magnetism is not merely a force, but a memory, the echo of creation still humming in the dark. In August 2017, the universe whispered in two languages at once: gravity and light. The first signal was not seen, but felt a ripple in space-time itself, captured by the twin detectors of LIGO and Virgo. They named it GW1 and Descent Ohansven. Just 2 seconds later, across the silent Gulf space, telescopes caught a burst of high-energy gamma rays, a flash so brief and fierce that it outshone whole galaxies. For the first time in human history, we had watched the same cosmic event through two eyes: the trembling of space and the blaze of radiation. Its source lay in the galaxy NGC 4993, a modest swirl of stars 130 million light-years away. There, two neutron stars, each the remnant core of a dead sun, had been spiraling toward each other for ages, losing energy to gravitational waves. When they finally collided, the impact released more power in a heartbeat than all the stars in the observable universe combined. From that titanic crash came not only light, but gold platinum, and the heaviest elements we know: the jewelry of the cosmos forged in violence. The event changed astronomy itself. We used to see the universe only through light. Now we could listen to its structure through gravity, hearing the creak of merging stars and the groan of bending space. Each new detection is a note in the cosmic symphony, the rhythm of matter colliding, merging, becoming new. Neutron stars are paradoxes made solid. They are the size of a city, yet weigh as much as the sun. Their crust is harder than any metal, their density so immense that a teaspoon of their matter outweighs Mount Everest. They form when a massive star explodes as a supernova, its outer layers hurled into space, while its core collapses under its own gravity. Electrons and protons fuse into neutrons, leaving behind a sphere of compressed nuclear matter, a star reduced to its skeleton. Their magnetic fields are trillions of times stronger than Earth's. Many spin hundreds of times each second, sweeping beams of radiation across the cosmos like lighthouses. We call them pulsars. Each rotation sends a pulse of radio or X-ray energy so precise that some astronomers use them as cosmic clocks. One such object, Jaminga, lies just 550 light-years away. It spins 5 times every second, yet its beam never reaches us in radio, only in gamma rays. Its name from Italian slang for "it's not there" fits perfectly: a beacon hidden in plain sight. Geminga races through space faster than sound travels through air. As it ploughs through the thin mist of interstellar gas, it gathers dust in its wake, forming a shockwave that glows faintly in X-ray light. Some scientists believe the material it collects could seed new worlds, tiny planets forming from the ashes of a dead sun. The thought is dizzying, a star that died giving birth to others carrying the raw ingredients of creation in its trail. Around such pulsars swirl Plerians nebulae powered by their winds of charged particles. Through telescopes they appear as faint halos or ghostly rings glowing with synchrotron light, the radiation of electrons whipped by magnetic fury. Each Plerian is a frozen moment of the supernova that birthed it, the memory of an explosion still expanding centuries later. But behind the beauty lies unbearable violence. On their surface, gravity crushes everything downward at 100 billion times Earth's pull. Atoms cannot survive there. Nuclei are squeezed into uniform seas of neutrons. It is matter stripped to its core nature at its most efficient and unforgiving. When two of these stars collide, as they did in 2017, they sometimes merge into a black hole, leaving behind jets that pierce the universe with bursts of gamma light. From such moments, galaxies are seeded with heavy metals. Our jewellery, our bones, even the iron in our blood were once part of those furious mergers. So when we study neutron stars, we are not merely gazing at distant catastrophes. We are looking at our own beginnings, the places where death and creation became the same act, where the universe learned that even destruction can be a form of birth. There are places in the universe where matter forgets how to be gentle, where gravity bends not only space but the rules of physics themselves. Among these places, neutron stars stand as the strangest, small, silent and impossibly dense. They are the final breath of massive suns, the skeletal remains of stars that have burned everything they could yet refuse to vanish entirely. Imagine a star 10 times the mass of the sun collapsing under its own weight. Its outer layers explode outward as a supernova, lighting up the galaxy for weeks. But at its centre, the core folds inward until protons and electrons are crushed together, fusing into neutrons. In that instant, what was once light and air becomes a stone of infinite heaviness, a single teaspoon of its matter weighing billions of tons. That is a neutron star, the universe's smallest giant. From a distance it may look tranquil, a faint sphere glowing in X-rays or soft blue light. But its calmness is deception. Beneath the surface rages a realm that defies every human metaphor. The outer crust is a thin shell only a few centimeters deep, made of atomic nuclei, squeezed into crystalline patterns of iron and nickel. Beneath that pressure becomes unbearable. Electrons are forced into protons, leaving behind a vast sea of pure neutrons. The atoms themselves disintegrate, reduced to their most primitive form. Deeper still in the star's core, physics loses its map entirely. Some theorists believe neutrons dissolve into a quark soup matter in its most elementary state, where protons and neutrons themselves break apart into the subatomic particles that built them. Others think exotic condensates, kaons, pions or hyperons form strange new matter no laboratory can replicate. The pressure here is unimaginable, 100 trillion times that of water at Earth's deepest ocean floor. The magnetic field is fierce enough to distort atomic orbitals. Any object dropped on the surface would hit it at 1/3 the speed of light, flattening instantly into its own shadow. And yet, for all this violence, neutron stars possess a strange order. Their magnetic fields align in vast arcs, their poles glowing with radiation. Every rotation sends out beams of energy like heartbeat pulses across the dark. To us they appear as pulses, spinning beacons that blink with the precision of cosmic clocks. Inside there is motion too slow for sight but too powerful for rest. At a depth of only tens of meters, the crust may melt into a liquid ocean of nucleons, a sea of neutrons and carbon ions churning at hundreds of millions of degrees. Its density is 10 billion times that of water. A single drop would outweigh a mountain. Fusion still burns here, faintly, quietly turning the remnants of hydrogen and helium into carbon. When the heat becomes too much, sections of this nuclear ocean erupt, releasing as much energy in 1 hour as the sun emits in a year. Astronomers detect these as X-ray bursts, bright and brief signatures of the star's trembling heart. The gravity on the surface is beyond comprehension, 100 billion times that of Earth. Nothing can stand against it. If mountains form, they are no taller than a few millimeters. A grain of dust falling from orbit would strike with the force of a hydrogen bomb. The atmosphere, if it can be called that, is only centimeters thick, a layer of plasma so hot that atoms cannot exist. Under such tyranny, even light struggles. Photons leaving the surface lose energy stretched by gravity's pull, until they emerge red-shifted, tired and thin. Time itself moves slower there, as if the star hoards not just matter, but seconds. And yet this monstrous precision carries grace. The structure of a neutron star is a masterpiece of equilibrium, a battle perfectly balanced between collapse and resistance. Every neutron pushes outward with quantum pressure while gravity pulls inward with infinite hunger. Neither side wins. The star endures poised forever between being and nothingness. In its silence, it becomes a symbol of endurance matter's final stand against oblivion. And as it spins cold and bright against the infinite dark, it reminds us that even in death, the universe keeps its most beautiful promises. In the quiet immensity of the galaxy, stars rarely meet. The distances between them are so vast that each one seems condemned to solitude. Yet sometimes gravity conspires to bring them together, two ancient suns drawn into an inevitable embrace. And when that happens, creation and destruction unfold in the same breath. Inside dense globular clusters where hundreds of thousands of stars drift like a swarm of fireflies, collisions become almost certain. Most are slow, silent mergers, two exhausted remnants spiraling inward until their cores touch. When white dwarfs collide, their combined mass may cross a forbidden threshold. The Chandrasekhar limit the point where gravity overwhelms electron pressure. In that instant, carbon ignites. A thermonuclear flame races outward, consuming both stars in a single flash, the hallmark of a Type Ia supernova. It is so luminous that for weeks it outshines entire galaxies. Then it fades, leaving behind only expanding gas and a single remnant, a neutron star, or if the mass is greater still, a black hole. Each explosion scatters heavy elements into the cosmic sea, calcium, iron, gold. Everything solid in our world was once part of such endings: the jewellery in our hands, the iron in our blood, the oxygen we breathe. Every collision writes another chapter in the autobiography of matter. Sometimes the aftermath is not an explosion but a transformation. Two white dwarfs may merge quietly, forming a temporary swollen object, unstable, spinning too fast for comfort. For thousands of years it glows with uncertain light before collapsing again, giving birth to a neutron star in silence rather than fire. And so even death has variations. Not every star dies screaming. For our sun, such violence is not its destiny. Its mass is too gentle for fury. But the universe is filled with giants, behemoths that live fast and perish young. Among them is Naus, the blue supergiant in the constellation, Puppis, burning at 40,000 degrees and shining with 600,000 times the sun's brilliance. Its mass, 45 times greater than ours, ensures a short life mere millions of years. Naus spins like a runaway racing through space, its outer layers peeled by stellar winds that could swallow entire worlds. Someday its fuel will fail, and its core will collapse into darkness. Naus will end as a supernova, its ashes perhaps collapsing into a black hole. Its death will illuminate the sky of another time, another Earth, with a light brighter than any sunrise. Even greater is Stephenson 218, the largest known star, a red hypergiant, whose surface would engulf Saturn if placed in our solar system. It burns not for billions of years, but for millions. Its vastness ensures its fragility. At any moment it could shed entire layers into space-building clouds of dust and colour across the night. When its end comes, the explosion will be beyond imagining, ripping apart its shell, leaving behind a compact remnant so dense it warps light itself. These giants are living reminders that the cosmos has scales of existence far beyond comprehension. They are the forges of the elements, the engines of cosmic renewal. Every generation of stars dies, so another may rise from its remnants. Even the gas lost by the Large Magellanic Cloud, even the dust ejected by hypergiants, will one day form the seeds of new suns. So in the end, there is no true death in the heavens, only transformation. Stars collide and merge, burn and fade, fall inward and rise again. And through every phase, the universe recycles itself, turning destruction into possibility. The night sky, glittering and calm, hides a storm of endings that are also beginnings. And perhaps when we look up at those distant fires, what we are really seeing is the memory of rebirth, the eternal conversation between light and darkness, between what was and what will be. In a quiet corner of the galaxy, a planet circles a dead star. Its name is WD 1856b, a gas giant the size of Jupiter, orbiting a white dwarf once bright as the sun. It lies so close that its year lasts only 34 hours. By all logic, it should have been destroyed when its parent star swelled into a red giant long ago, and yet it endures. Astronomers offer two stories of its survival. Perhaps the planet was swallowed stripped by heat and friction, then released when the star collapsed its scars hidden beneath calm motion. Or maybe it came later, migrating inward after the chaos drawn by gravity into this improbable orbit. Either way, WD 1856b proves that even after stellar death, stability can return, a world reborn from ruin. From that quiet survivor, our gaze turns to the opposite extreme heat and its limits. If absolute zero is the end of motion, what marks the end of existence itself? The answer is the Planck temperature, about 142 million trillion degrees C. Beyond it, space and time blur. Physics itself dissolves. It is the temperature of the universe's first instant, when matter and energy were one. Human experiments have brushed the edge of that fire. Inside, the Large Hadron Collider particles collide at 10 trillion degrees, briefly melting atoms into quark, gluon plasma, the same substance that filled the newborn cosmos. For an instant shorter than a breath, humanity recreates the heat of creation. But in the vastness of space, nature surpasses us easily. Ionosulfur volcanoes rage at 300 dig. The sun's corona burns in the millions. Newborn neutron stars reach 100 billion. And in quasars near black holes, gas spirals upward of 10 trillion degrees before fading into light. Between a frozen survivor like WD 1856b and the unimaginable heat of creation lies the story of endurance. Some worlds live through fire, some laws survive collapse, and through every temperature, every threshold, the universe keeps proving a single truth: that existence is not fragile, it is patient. In the constellation Orion, Betelgeuse flickers a red giant nearing its end. One day it will explode as a supernova, shining brighter than the moon and turning night into day. For Earth, it will be only a spectacle, not a threat. 600 light-years make its fury harmless. But if such a blast occurred closer within 100 light-years, the story would change. The radiation would strip our ozone, flood the skies with ultraviolet fire, and life would fade under invisible light. It is the kind of ending written quietly into the history of extinction. Yet from every supernova, the universe begins again. Each explosion forges iron, gold, and calcium, the elements of future stars, future worlds, and us. A dying star is not the end of light, but its renewal. We are the calm after such explosions, the dust that remembered how to shine.